Right. Variation of parameters in general. Okay. So let's suppose that you have ay double prime plus by prime plus cy equals the function f of x. We're trying to solve this using variation of parameters. Of course, the reason being that somehow the function on the right has some really messy derivatives, and therefore method of undetermined coefficient doesn't work for us. Okay? In that case, how do we do this? Well, so in general, what you do is you first start with y complementary, and if you find the complementary, you're going to have two solutions, right? C2, Y2. Because it's a second order, the complementary will have two solutions coming from the characteristic equation. Now, what do? What do you take your yp to be?
U1 of x, y.
Right. U1 of x. So these are functions of x. U2 of x. It's like this. Okay, you have a U1 replacing the C1. So from a constant, I promote it into a function. So it's more complicated. And the idea is to plug this into the left side to make this thing work. And along the way, when we first find the derivative, we have the assumption that one part of the derivative should add to 0. So we will be getting u1 prime of x times y1x plus u1x y1 prime of x. And then if I differentiate this, it's going to give me u2 prime of x, y2 of x, and also u2 of x, y2 prime of x. That's what I'm going to get through the product rule. And our first assumption is that this should equal to 0. Okay, so this will be always the condition that we assume. For any variation of parameters question, we will always assume that u1 prime of x, y1x, plus u2 prime of x, y2x will be 0. That's the condition. That's what we always assume. All right, next, we differentiate this yet again to get y double prime of x as u1 prime of x, y1 prime of x, plus u1 x, y1 double prime of x, and then u2 prime of x, y2 prime of x, and u2 prime of x. Actually, u2 of x times y2 double prime of x. Once I have those derivatives, I plug it into the original equation. What happens then? I'm going to get this thing multiplied by a. So everything, because of this a, everything will be multiplied by a. So I'm going to get a times u1 prime of x, y1 prime of x. Okay, and then plus u2 prime of x, y2 prime of x, plus a times, actually, let's write it. I'll just multiply by a. Okay, so that's what you get for a times y double prime, and now we have by prime, which is this one. This part is 0, so y prime of p is only this part, which is multiplied by b. And then finally, c times y, so c u1x, y1x, plus c u2x, y2x. Okay, so this, the left side of this, or this equation now becomes this humongous equation. And because y1 and y2 are the complementary solutions, you're going to see a lot of cancellation. What do you think will cancel? So think about it this way. If I plug in y1 on the left side, what would you get on the right side? For example, my question is, what's a y1 double prime plus by1 prime plus cy1? What would this give me?
0.
That's what it means to be a complementary solution, right? Same thing for a y2 double prime plus by2 prime plus cy2. It'll also be 0. Now, do you see this here? If you take this much and factor out the u1, what do you get? A y1 double prime plus by1 prime plus cy. Right? So what do you get?
0.
0. So this much is 0. How about this much? If you factor the u2 out, you get this much, right? So that's gone. All this worked because we were using the complementary solution and we were modifying it. Okay? That's why the variation of parameters will always work. Okay? Those cancellations that you get with using this method, they're not magic. It's just that way because we're using the complementary. Okay? So from all that, what we're getting is that if I divide a to the other side, we get the following equation. We get u1 prime of x, y1 prime of x, plus u2 prime of x, y2 prime of x equal to f of x divided by a. Okay? And now we have, I should have written this in red because now we have two systems, right? I have one equation for u1 prime and u2 prime. I have another equation for u1 prime and u2 prime, which can be written as a matrix form of equation, right? Can you write this equation in matrix form? See, you're thinking of u1 and u2 as your unknowns. u1 prime and u2 prime are the ones that you want to find out. Now, what's the coefficient matrix then? These two, right? So we have y1, y2. Okay? And here, the coefficients are y1 prime, y2 prime, equal to what and what?
0 and f of x over a.
Okay? Now, if you forgot what matrix is, let me give you a quick explanation of why this is same as before. You multiply matrices by doing across down, across and down, right? So you do y1 times u1 prime, y2 times u2 prime, and you add them. That's what you get as the first element. So if I do across down, then I get exactly y1 times u1 prime plus y2 times u2 prime. What should that equal to? It has to equal to 0, right? That's why I have a 0 here. And then I do across down here, y1 prime times u1 prime, y2 prime times u2 prime. You have to add them, which is exactly this much, right? What is this supposed to equal to? Fx over a. That's what it should equal to. All right? That's why this matrix form of the equation is equivalent to the system. Okay? Now the reason I'm using matrices here is because if you have a matrix, then it's easy to write down its solution using the inverse of a 2x2 matrix. All right, I'm afraid that you probably forgot the 2x2 matrix inverse also, so let me write it down here. If I have A, B, C, D, the inverse of that matrix is you first divide it by AD minus BC. What is this thing called, AD minus BC?
The determinant.
Determinant of the matrix, right? And then you're supposed to switch these two around. A and D should be switched around. And the off diagonal elements, you have to negate them. Okay? So that's the inverse, which means the solution of this is just this. You have to divide, right? You have to multiply the inverse of this matrix to the other side to solve it. So this has the easy solution according to our thing here, which is I guess I wanted to erase this part. Erase this part. Yeah, let me erase this too. Erase this. Erase this. Okay. So my solution for this is u1 prime, u2 prime equals to first the determinant of this thing, which is 1 over y1, y2, y1 prime, y2 prime, determinant. We've seen this determinant before, right? What is this thing called? You have two functions, and it's derivative, and you take the determinant. Wronskian of two functions. Okay. So somehow magically the Wronskian appears, and we have to switch these two around. So you have y1, y2 prime here, y1 here, and negative y2, y1 prime, negative y1 prime, times 0 and f of x over a. Now, since this looks a little annoying, let's just rewrite this as f of x tilde. And then it's easier to write. Let's see what we get if we actually multiply. Across down. 0 times this is nothing. This times this gives you I'm just going to write down W for this, for the Wronskian, okay? Because that's the Wronskian. I'll cross down this times this is what you get. So on the top you get negative y2 f tilde. And for this times this, 0 times this gives you 0, y1 times this, you get y1 times f2. And we're almost there, because now you can multiply w, 1 over w inside to get negative y2 f tilde over w, and y1 f tilde over w. You're almost there. Let's see, that means u1 prime is equal to negative y2 f over w, and u2 prime is y1 f tilde over w. And now we have to plug those back in here. Now, since we have u1 prime, to get the u1, you have to integrate, right? So let's write down the integral. So our final conclusion is that y of p should be y1 times u1, which is the integral of this thing, right? So it's negative y2 f over w dx plus y2 times u2x, that's again an integral, which is y1 times f over w dx. So here's the result of our formula. This is the formula that you get from variation of parameters, and I guess we should at least come up with one possible example. Without it, it'll be just too much, right? So let's think about the following example. If I have y double prime minus y prime minus 6y equal to let's just put something wild here, square root of x. Again, that's impossible to solve using method of undetermined coefficients because square root of x has derivatives which never end, right? Okay. Now, what are the two solutions in our case? R squared minus r minus 6 equal to 0, r minus 3, r plus 2 equal to 0, right? So you have 3 and negative 2, which means you have your y1 as either 3x and y2 as either negative 2x. That's your two complementary solutions. Now let's apply this formula that we have. Okay, first you have to compute the Wronskian, which is simply the two functions and its derivatives. So if I differentiate, this is 3 e to the 3x, negative 2 e to the negative 2x. So I write their derivatives. That's what Wronskians do. And that gives me AD minus BC gives me negative 2 e to the x minus 3 e to the x, so negative 5 e to the x. That's my Wronskian. And when I was doing this, e to the 3x times e to the negative 2x, 3x minus 2x, that's 1x, right? So that's why I got that. Okay? Try to follow that. And I'm almost there. Now we know that the particular solution is y1x e to the 3x times the integral of negative y2, it's this one, e to the negative 2x times the function f of x. Now, this f tilde is supposed to be the right side divided by the coefficient of this thing, but it's 1. In that case, we don't have to worry about this tilde. It's just the function of the right, okay? Divided by negative 5 e to the x dx plus e to the negative 2x times y1x e to the 3x times square root of x divided by negative 5 e to the x. And therefore, we get e to the 3x. Negative negative cancels, and you get 1/5. So it's 1/5 times the integral of negative 2x minus x is e to the negative 3x. So it's square root of x times e to the negative 3x dx. And then here, it's plus e to the negative 2x. Again, you have a negative 1/5. And then integral of e to the 2x times square root of x dx. So that's the particular solution. Now, one more thing I want to say is that when you do the integrals, you get the constants, right? You have plus c, right? So if I call the constant that you get from here as plus c1, and this one is plus c2, then you get c1 times e to the 3x. There's division by 5, but c1 over 5 can be thought as a c1. So you have c1 times e to the 3x plus c1 times e to the negative 2x, which contains the complementary solution. So not only you can say that this is your particular solution, but you can just say that this is the solution, the entire solution of this given differential equation. Now the reason I stop here is because these integrals cannot be done. You can try any kind of integrals that you know. You'll find that it's impossible to do it. The integrals cannot be written in closed form. I believe if you use some transformations, you might be able to write down the solution in error function in some way, but I don't know. It's an integral where you can't proceed further. But the achievement is that at least you wrote down the solution in an integral form, and when it comes to finding the solution, just trying to find the numerical solution of this is actually harder and less stable than trying to find the numerical approximation of this thing. So this is more preferred. Yes?
So that would, in the red, that would get full credit on a test.
Yes, yes. So when this is impossible to integrate.
Okay.
But there are some cases where you could integrate, so you have to distinguish between them. Right, that's
But if you do integrate,